Prop your finger. That smells right.
This feels like a rocket launch, yeah? Like you have that thing going and it makes me nervous.
Hi everyone, we are ready to begin the presentation of Shankar about machine learning using Python tools. Shankar is a student and worker for the researcher for the University of Singapore, where he does research for the acoustic research laboratory about communicating robots underwater. And well, turn off your cell phones and enjoy.
Thank you. So this is introductory talk. The aim of this talk is to give you like a broad overview of machine learning, and at the end of the talk you should have an idea of the broad classes of algorithms that are there in the field of machine learning and have enough insight so that when you want to build your own machine learning systems, you know where to look. So let's begin. What's machine learning? So machine learning is basically if you're trying to write programs without explicitly stating all the rules of the program and instead like deriving some of the rules from data, machine learning literature is concerned with how do you make efficient use of data to generalize. So for example, if you want to detect spam emails, it's really not practical to write a program that will like identify every single possible spam email in the world. Instead, what is commonly done is you collect a large corpus of emails and you have them tagged as spam versus non-spam, and you have a program that ingests all of this data, and then when it gets a new email, it's able to predict whether it's a spam email or not. So machine learning is the field that's concerned with building programs that operate on data and do intelligent things with it. So the first broad class of machine learning algorithms are called supervised learning algorithms, and these operate on data which have labels. So the spam versus non-spam is one example. Another example would be sentiment analysis of text. So for example, if you have like a lot of user reviews and you have them labeled as positive, negative, or neutral user reviews, it's possible to write a program that will take all of this corpora, analyze it, and then when it reads a new review, it's able to automatically tell whether it's a positive review or a negative review or if it's neutral. So the important thing for a supervised learning algorithm is that you feed it data and that data is labeled. So the labels can be anything. It can be user reviews, or it could be like a number. If you're building price models, it's a number, and so on. The other important class of algorithms are unsupervised learning algorithms, and these operate on data without any labels. So you just feed it raw data, you have no labels, and you can do things like find clusters in your data and like find other patterns and relationships within them. So for example, Google News does something similar. What it does is that if there are a bunch of related news stories, it doesn't like show you 3 different links for 3 news stories which are really about the same event. Instead, it can identify that, all right, like these 3 stories are all about the oil spill, and it just gives you like one link. So that's basically clustering in action. People use clustering algorithms to do like market segmentation and find communities in social networks and things like that. The other major class of machine learning algorithms are recommender systems. So when you go to Amazon and you are looking at the web page for a book, Amazon says that if you like this book, then you'll probably also like these other books. And these are actually really important in industry because they like drive sales quite a lot. Netflix does that. It gives you movie recommendations depending on your previous history of borrowing movies from Netflix. So To get started with machine learning, the prerequisite is that all of your data, the real world is, you need everything in the world to be represented as numbers and to be more precise as vectors. So for example, if you have housing data, let's say you have a long table with house price and with house sizes, and if you plot them on a 2D plane like this, every data point is basically a vector, and the vector has like two numbers. This number is the house size, and this number is like the house price. So so if you're operating on numerical data like this, it's easy to represent it as vectors, but if you're operating on text, for example, then it's a little bit more complicated, and if you're operating on images, it's a little bit more complicated. But the first step in building any machine learning pipeline is to represent the real world in vectors, and this has a few advantages. So you can do things like, the moment you have your data in vector form, you can do things like you can find out how similar are 2 points. So the similarity is basically the Euclidean distance between them, or it could be cosine similarity. So similarity has different notions, and all of these routines are common in Python. You can do numpy.euclidean, and that will give you the Euclidean distance between two vectors and so on. And this is useful because, let's say you're Amazon, and this is like, and suppose each of these dots represent like one of your products, and one of your users is like looking at this. The simplest recommender algorithm would basically just recommend other products that are located close by, because they are similar. So this is like the first step in the machine learning pipeline. Some notation that's common in machine learning literature that's useful to know is that when you make measurements, you represent them in like a huge table, in a huge matrix actually, and I call this big matrix as X, and it consists of a number of rows, and each row is basically one record or like one observation. So for example, if you have housing data, so this will be our running example throughout this talk. If you have housing data, and let's say you like measure a number of things, you measure the area, the number of bedrooms, and so on. So each of these things is like a feature, and you write down these numbers in a row, and that gives you like one vector, x1. The t here is a transpose, because usually vectors are column vectors. You write them like this, and a transpose of a vector is just you rotate it. So you just stack all of these vectors, stack each of these observations. So each observation is a vector, and you stack all these observations one over the other, and you have this huge matrix, and that matrix is X. And to do supervised learning, you have another matrix Y. Here it's just like a one column matrix. It could be like many columns depending on the nature of the problem. And what you do in supervised learning is that you need to figure out a function h. So this function h, it takes in as input a new observation x new, and it will give you like an answer y, which is like its prediction. And figuring out this h, that's what the learning in machine learning is about. H is also known as the hypothesis function, so as the name suggests, it's like your hypothesis. I'll run through a quick example of how you would represent, for example, text as vectors, because I guess if housing data is numerical, and that naturally lends itself to a vector representation, but text is a little bit more complicated. So one way to do it would be, let's say you have n documents, and you have m terms. So each term is like a unique word across all other documents, and you have a 1 or 0 depending on whether document 1 has term 1 or not. So this is a bag of words representation. Another common representation is what's called the TF-IDF representation. So TF-IDF stands for term frequency inverse document frequency. There's a little bit more complicated representation. It basically has two parts. So it consists of like one part called the term frequency, which is basically the frequency of that term in that document. And then there's this big log number. This number is calculated by just doing some arithmetic on counting, by just doing some arithmetic on all the terms in all your documents, and it gives you a measure of, it has some nice properties. So what happens is when you compute all of this, in this matrix, instead of 1 and 0, you have numbers between 1 and 0, and that's like a more refined measure of your data. So To do all of this in Python is you have this project called GenSim, and that does this really well. So in GenSim you can say documents is this. So this is a toy example. Each document is just a sentence, and then you can just initialize this TF-IDF object, which will like give you TF-IDF vectors from text. So this corpus object is derived from the documents. You just feed it, and then when you like print, when you print it, you basically get the vectors. So every row here is a vector corresponding to a document. So just simple to use libraries in Python. You don't have to like do the entire TF-IDF computation by hand. Images as vectors, this is easy to do. If you want to represent an image as a vector, one option would be, like the simplest option would be to just represent all raw pixel values in like one giant vector, or you could do things like average, find out the average of like the neighboring pixels for each pixel, and in the image processing community people come out with like various ways to represent an image as a vector. So depending on your application, like you'll have to figure out a suitable way. Scikit-learn is the machine learning workhorse of Python. It's like the main Python project that has a huge number of machine learning algorithm implementations. And some sample code from it, it's good to look at that. So here you have x, y is equal to iris.data, iris.target. Iris is a popular data set that's commonly used in many machine learning textbooks to like illustrate and benchmark different algorithms. So iris.data gets assigned to x, and x is like that giant big matrix, and iris.target is the y matrix. And you can do things like from sklearn.svm import linear SVC. So this is basically importing like one machine learning algorithm, and you can say CLF or classifier is equal to an instant of this algorithm. So it's just like 4 lines of code and you have like machine learning algorithms on your fingertips. So the simplest supervised learning algorithm is probably linear regression. It's definitely linear regression. So coming back to our house price data example, I have a bunch of points. So this is size versus price. And the goal is to build like a predictor which when given a new house, if you're told the size in square feet of a new house, you want to be able to predict how much it's going to cost. The simplest way to do this would probably be to fit like a straight line through these points. And this is like the equation of a straight line. So h of x, so h is the function that we learn. It takes as input x is the size in square feet, and it just does some multiplication and addition. It multiplies x1 with theta 1 and theta 0, and depending on the values of theta 0 and theta 1, you can get different lines. So h is the function, and it has like 2 parameters, theta 0 and theta 1. And depending on the values of these parameters, you could get either a good fit, which is this one, or you could get like really horrible fits. Like this line really makes no sense at all. So the aim in supervised learning is to learn the values of theta 0 and theta 1, which are good for your problem. And how do you find out good values for theta 0 and theta 1? In order to do this, the way it's done is that you measure errors from the prediction. So suppose this was our model. This was our suppose the algorithm suppose you say that okay, this line is a candidate line. If you want to evaluate how good this line is, you measure the prediction error. So suppose you had a point somewhere here. If someone told you that the size of the house was, let's say, 2,400 square feet, your model would output a value over here, and the real value is this one. So you have a little error here, and the value of this error is basically this term h of x minus y, this difference squared. We square it because negative numbers, you don't want negative numbers in the errors. So you square that, and you do that for all the points. So this summation here basically tells you that you find out what's the error for all the points, and you normalize it by the number of points you have. And so this expression, which gives you like the average error in your model, is termed as a cost function. So as the name suggests, it's basically the cost you pay if you go with this model. And the aim is to always like have the least cost, because the least cost is basically same as least error. So just to recap, the way linear regression works is that you have a training set, and then you have a learning algorithm which operates on this hypothesis function h, and input is the size of a house, output is an estimated price. So how do you find the right parameter values for theta 0 and theta 1? In Python, it's basically just like one line. You do this clf.fit x comma y, and it will figure out what's theta 0 and theta 1. And when you have a new data, let's say you have a new vector x new, you can say clf.predict. So it will predict the value of x new, and it will give you the answer. So to give you more insight into how you actually arrive at these values, I will go through a simple one-dimensional example, and then it will be clear how to do that in like many dimensions. If you plot theta versus the error, you will get a graph that looks like this. So for some value of theta, the error is like really small, and for all other values of theta, you have like large error. And what you do is you do what's called a gradient descent. So let's say you randomly pick a point, let's say this one, and then you update it as per this rule. What this rule says is that from this point you subtract a number. This number is equal to alpha, which is like a small constant, it's not important, times the partial derivative, like times the derivative at this point, which is some number. If you do that, you go from this red point to this one. If you randomly happen to pick a point in this area, then you will begin to move in this direction. So no matter where you pick a point, you will eventually it will eventually converge over here, and then that value of theta is your answer. So this is the mathematical intuition behind what actually happens. You don't have to do that by hand. You can use the libraries. In the more general case, you don't just have one parameter, you have like many parameters, because you might be measuring things like area and bedrooms and neighborhood quality and so on, and you'll have like a parameter associated with each of those. And you don't have like a curve, you have a surface, and you find the minimum value of that surface. So putting it all together, linear regression works this way. Training set, learning algorithm finds out the value of h, input are a bunch of vectors, output is another vectors. The interpretation for these input and output vectors are really dependent on what you're trying to do. Like on your, in our case it's house data, in your case it could be like really anything. I'll just touch upon a different form of regression called logistic regression. To motivate this example, consider a tumor detection program. So let's say you have data from a hospital that tells you tumor size versus whether or not it's malignant, and it basically looks like this. So like small tumors are not malignant, and at some point they begin to be malignant. And what you want to do is build a program that will take as input tumor size and will tell you whether or not it's malignant. To do this, you can use the same principles that we just talked about, except that you change the form of h. So like I said, h is the hypothesis. So if your hypothesis is that, all right, I think the data is like, just by looking at it, you can say that it goes like this. It's something like this. So you can like write out a new function for h, and h is this function, this big looking function, which is actually not complicated. It's just a fraction, 1 over 1 plus e raised to minus z, and this number z is a function of x. So x is like your data, and then you just multiply and add it by a bunch of things, and then you get h. So instead of trying to understand what h is, it's easier to look at its graph. So if you plot z versus h, it looks like this. It's basically an S curve. And if you learn the right values of theta 0 and theta 1 for your data, then you can just input, when you have new data, you can input it here, and then you can get as an output what is the likelihood of it being malignant or it being benign. So h has a few nice properties. It always lies between 0 and 1, because in the previous example, like linear regression can give you values from anywhere minus infinity to plus infinity, but doesn't make sense in this case because you just have like y can be just either 0 or 1, so you can like change h and make it take just values between 0 and 1. If you do that, you can also change the cost function. So the cost function in the previous example was basically the sum of errors for every point, and you like average them. Here the cost function is slightly different. I have, instead of writing the equation, I have like plotted it. So if you plot h, and there are two plots. So this plot corresponds to the y equals 1 case, that is the cancerous case. So what this plot tells you is that if it's cancerous, and the output from your classifier also says that it's cancerous, the cost is low. But if you make a mistake and you say that it's benign, then you like play a very high cost. And it flips in the other case, like if it's benign and you make a mistake and you say it's cancerous, then you pay a very high cost also. So using the same principles, you can minimize this cost function, and then you arrive at theta 0 and theta 1, and then you just plug that in over here, and now you have a program that can tell you, given tumor size, whether or not it's malignant. The point of this is that depending on how you change h and how you change the cost functions, you can like come out with really complicated models, and you can learn relationships among really different, much more complicated data than what you saw here. And really supervised learning is about developing new algorithms that have new forms of h and new forms of the cost function. So the state of the art today in supervised learning is probably neural networks and support vector machines and random forests. As a programmer, you don't necessarily need to understand the mathematics behind how all of this work. The general principle is same as a regression. You try to like minimize errors basically. And in scikit-learn, you can do things like from sklearn import SVM. So SVM is like one of the state-of-the-art machine learning, supervised learning algorithms, and then you have x and y. You say classifier is SVM, and then you say classifier.fit x comma y, and it finds out what are the parameters for your data. That's x and y. And then you just do clf.predict, classifier.predict with a new vector, and it will tell you what the prediction is. So as a programmer, it's relatively easy to use this, and the principles are basically simple. So that was supervised learning. The second important component is unsupervised learning. In unsupervised learning, you have data, but the data doesn't have labels. So what can you do with unlabeled data? The first thing you can do is you can cluster them. You can find where they are clustered basically. So like I said, Google News will give you like one link for related news stories. So to do things like that, you do clustering. By far, the most common clustering algorithm that's like really widely used is the k-means algorithm. And I will walk through how k-means works for a 2D case, and then it's really easy to generalize it to an n-dimensional case. So what you do is, let's say you have like a bunch of vectors, 2D vectors, you plot them, and let's say you decide that I want to cluster these into 2 clusters. I want to cluster my data into 2 clusters. You randomly pick like 2 points, a blue and a red point, and I call these cluster centroids. And after you randomly pick them, you assign your data to one of the 2 centroids. So basically what you do is, if any point is closer to the red one than to the blue one, it becomes red. Like whichever is closer to the blue one, that becomes blue. Whichever is closer to the red one, that becomes red. Once you do this step, then you move the centroid again. So essentially, k-means consists of basically starting with two centroids, and then like splitting your data and like assigning them to one of the 2 centroids, and then you move them to like the center of all the red points, and when it moves things change. Some of the blue become red, some of the red become blue. So you do this back and forth for a couple of times until the centroids don't move anymore, and now you have like basically 2 clusters in your data. You have, this is like one cluster and this is like another cluster, and when the centroids don't move, you know that your algorithm has converged. The other important unsupervised learning algorithm is dimensionality reduction. Often, it's not uncommon in many machine learning applications to have like really high dimensional data, like maybe 1,000 or maybe a few thousands of dimensions. So I'll just give a toy example. Let's say you are measuring the length of something, and you have plotted like the length in centimeters and its length in inches. And this is really redundant, right? You just need one measurement. And you don't, so it's useful in this case to, instead of having 2 dimensions, just have like one number to represent each of these points, because it's really measuring one thing. This might seem like a contrived example, but in reality it's not. When you're working with large engineering teams, like one team might be measuring things in its own way and like giving like a huge data host to you, and another team might be measuring things in a different way, and then you might get the data feed from them, and they might be measuring the same things, and there might be quite a lot of overlap. And to feed and then to feed your machine learning algorithms downstream, you don't want, like, you just want one measurement. You don't want like redundancy in those measurements. So dimensionality reduction allows you to like throw away redundant dimensions and just keep what you really need. The way it's done is that you have these points. Let's say you draw a line again, like you draw this green line, and you project each point on the green line. So like this green guy, it gets projected here, and this is, so this figure, this is basically the projections of each of these points on the green line. And then you can just report this distance, z1. So now you need just one number to represent each of these points instead of like 2 numbers over here. By projection, what I mean is, just to be more precise, let's say you have vector A here and vector B. You draw perpendicular here, and this green part, this is the projection of A on B. So you think of it like a shadow of A on B, like how much shadow does A create on B. That's one way to think of it. Dimensionality reduction, you could, of course, it's useful to do this to visualize data. So let's say you have a 3D point cloud, and let's say you have if you can find out 2 vectors, z1 and z2, these 2 vectors define a plane, and you can like project each of these points on the plane, and then instead of having a 3D point cloud, you can just show them on a 2D plane. So in order to do dimensionality reduction, the most common algorithm that people use is principal component analysis. And the way principal component analysis works is as follows. Look at this 2D case. Here you have these points, and you have the projections. When you go from 2 dimensions to 1 dimension, you lose some information because you make errors. And this blue part here, this is like the projection error. And you might have guessed what principal component analysis tries to do is it tries to minimize this projection error. The same thing happens in the 3D case. You have a 3D point cloud, and then you have projections on a plane. So for this point, for example, it gets projected here in the green line, and this part is the projection error. And every point will contribute to some amount of error, and principal component analysis basically tries to find the line or the plane that will minimize errors. And I won't go through the details of how you do the minimization, but in scikit-learn, you can just do these things. You can say PCA is equal to decomposition.pca, and then you say PCA.fitX. X is a 3D, X has 3 dimensions, and then you can do PCA.n components is 2, which is basically telling the PCA objects that reduce it to 2 dimensions, and it'll go from 3 to 2. You have some extra things over here. I'll explain what it is in a second. If you do PCA.explained variance, you get like 3 numbers. So if you go from 3 dimensions and you stay in 3 dimensions, you don't lose any information. But as you start to decrease the number of dimensions, you start to lose more and more information. And exactly how much information do you use? That's given by these numbers. So if you examine these numbers, you see that the last number is something raised to minus 32, which what that tells you is that really most of the information in your 3D data set here can be represented with just 2 dimensions, because you see this 2.1, this 1.9, and this one is like 8 raised to minus 32. So throwing away the 3rd dimension, you won't lose much information, and so that's the interpretation. One of the more important applications of PCA is in information retrieval for text. It's this algorithm called latent semantic indexing. It's basically a variation of the PCA. Typically, when you deal with text data, you have very high number of dimensions, because the number of dimensions is basically equal to the number of unique words across all documents, and that can be like tens of thousands or like thousands. And latent semantic indexing allows you to go from like a few thousand dimensions down to like 200 or 300. What that does is that it throws away words like the, and commas and so on. So like those don't really contribute to much. Those don't really contribute much, and you just keep the more important words. You can, as a programmer, you can just use gensim this way. You just say LSI is models.lsi. You initialize a latent semantic index model, and to this LSI you just feed it this document, human computer interaction, and it computes vec LSI, which is a vector, which is an LSI vector for this document. And then it's easy to do similarity queries. So for example, this one, doc is equal to human computer interaction. This is the query. The query gets transformed to a vector over here, vec LSI, and then you just do a little bit of transformation, and you have sims here. And the previous, a few slides ago, I had a bunch of other documents, which are these, EPS, user interface management system, and so on. So if you query the sims object and ask it to like list out in order of relevance other documents that are closest to the query is human computer interaction, it lists these things out. So it's one of the interesting things that you notice here is that the query document is human computer interaction, and if you like look at the first two results, it's EPS, user interface management system. The second one is the first one is the EPS, user interface management system, and it seems like a relevant answer, and it's interesting because there's no keyword match. So if you do things like keyword matching, or if you try to compare just TF-IDF vectors, you won't get results like these. So this is like a good example of dimensionality reduction in action. Next part is I'm going to talk about recommender systems, and here is like a toy example again. This is a movie recommendation problem. So let's say we have like 5 movies in our library: Love at Last, Romance Forever, Cute Puppies of Love, Non-Stop Car Chases, and Swords vs. Karate. And let's say you have four users, A, B, C, and D, and each of them have like they've given some rating for some movies. And the problem is to find out what would be the value of these guys. Like what would Alice rate Cute Puppies of Love, or what would Bob rate Romance Forever? So that's the recommendation system problem. If you think about it, one easy way to solve this is to just do supervised learning. Suppose you had like 2 special numbers associated with each movie, which tell you how romantic or how much of an action movie it is. So for example, Love at Last, if you have like a romance coefficient for Love at Last and an action coefficient for Love at Last, and if you have that for all movies, then you can basically do a linear regression. In the case of, in this example, like when you have movies or books, this is obviously not realistic, but if you have things like video cameras or electronic items, then you can use these kind of methods. You can list out what's the zoom and how good is your lens, and so on. So assuming you have these numbers, which is x, you can basically do a linear regression and find out what is theta for each user. So basically you train a model for each user. So let's say Alice, she is rated like 4 movies, and each of these, so this is movie 1, movie 2, movie 3, movie 4. So movie 1 is 0.9 and 0, and its rating is 5. So this is basically a supervised learning problem. You feed all of this to a linear regression, and then it will learn the coefficients for Alice, and when a new movie comes in, you will be able to predict how well will Alice like it, or or whether she'll not like it, and so on. However, the state of the art in recommender systems is actually not to do supervised learning, it's collaborative filtering. In order to explain how collaborative filtering works, just for a moment consider the inverse problem. This problem is, here in this slide, you can think of given x, so x are these numbers, given x, can you learn theta? So theta corresponds to a user. So x corresponds to the movies and theta corresponds to the users. So given x, can you learn theta? The answer is yes. Given x, you can learn theta, just do linear regression. The other way around, given theta, can you learn x? Suppose someone told you for each of these users how much action movies do they like, and how much romantic and how much action movies do they like. So for example, Alice, she seems to like romantic movies a lot, but she doesn't seem to like action movies. So the romance coefficient is 5 and the action coefficient is 0. So if you have this data, suppose you had this data for all users, could you come up with, could you fill up this table, which is the romance and action coefficient for every movie? The answer is yes. You again basically do a linear regression. You just fit the data the other way around. But in reality, you have neither x nor theta. In most cases, you have neither x nor theta. And that is where collaborative filtering comes in. What you do is you learn the values of x and theta simultaneously. And the way that works is that you start with some random values for theta, and you minimize errors, and you keep minimizing them, and then you arrive at some value of x. And then you use that x, and then you again do an optimization, and then you arrive at a new value of theta. And then you do this back and forth a bunch of times, and eventually values of x and theta will settle, and then you can do linear regressions in any direction you want. So that's how you do collaborative filtering. The last part of the talk, and probably the most important part, is testing and debugging your machine learning algorithms. So how do you know how good is your algorithm? The most common way to do this is to basically split your data into two sets. You have a training set and a testing set, and you fit your model, find the right values of theta and so on the training set, and then you feed your model with this data, which is from the testing set, and you will have some error, and that error is a good estimate of how well your model will perform for unseen data. A common mistake when many machine learning practitioners do is they report the error on the training data. So on the training data you have some error, and they report that error as the expected error on new data, which is not true. Because your model has already seen this data, and the error that you get from the training data is a overly optimistic estimate of the error that you're going to get on unseen data. So the key is to always, if you want an estimate of how well your algorithm will perform, always feed it unseen data. So you train it on some training data, but the test data will give you a number that's a good estimate of how it will perform on unseen data. So this splitting is important. The other problem that you usually run across is a model selection problem. So in linear regression, the simplest model that you could fit is probably a straight line. So like theta, and it has just two parameters, theta 0 and theta 1. You could do something a little bit more sophisticated, and you could fit a second degree polynomial, and a second degree polynomial can curve. Or you could do something even more crazy, and you can like fit like a 4th or 5th or 10th degree polynomial, which can like really go in any shape that you want. These are nth degree polynomials for a linear regression in a linear regression model, but in general you can make your models more and more complicated, and they can like learn more and more complicated surfaces, like arbitrarily complicated surfaces can be learned. Which of these is actually a good choice? Which one should you use on new data? So picking a model is also an important it's an important step in the machine learning pipeline. And the way you do that is, now you need 3 splits of your data. So you have a training set, you have a cross-validation set, and you have a test set. And the way it works is as follows. Let's say you are considering 10 models, and they are like, as you go from 1 to 10, they become increasingly complex. You can use the training data to learn the parameters of each of these models. So for every model, you feed it the training data, and then it learns its parameters, and now you have like 10 models available. And now you want to pick one of them. You pick the one which will give you the least errors on the cross-validation set. So it has not seen the cross-validation data. So you take every model and you feed it with cross-validation data, which is this one, and then you see how much error it gives you, and you just pick the model which will give you the least errors on the cross-validation set. The test set, as usual, will tell you how much error you can expect on unseen, how much error each model can expect on unseen data. So essentially what we've done here is that we have broken down the process of learning parameters into like 2 steps. So like you learn all the you learn all but one parameters using the training data, and then the last parameter to learn is which model to pick. And to do that, you consume this data, and then the final data is reserved for like reporting how much error that will have. The other important diagnostic test that you can run when you're building a machine learning pipeline is a bias versus variance diagnosis. So usually if your learning algorithm is not performing well, it's either because of a high bias situation or it's because of a high variance situation. So a high bias situation occurs over here. You have data, let's say, that looks like this, and you're trying to fit a straight line, and you're obviously going to have quite a lot of errors. It's called a high bias situation because your hypothesis, this one, is biased that the data fits a straight line in spite of being presented evidence to the contrary. The other extreme is a high variance situation where you have this crazy curve and it basically goes through every single point, and when you have new data that comes in, this is not going to generalize well, and then you'll have errors again. And this is a high variance situation. So distinguishing between high bias and high variance situations is important, and the way you do that is basically you use what's known as error curves. So you plot 2 curves. This is the degree of the polynomial, and these are the errors, and you plot the error on the training data, and then you plot the error on the cross-validation data, and this will tell you whether it's high bias or high variance. So if you're in this regime, it's basically high bias. If you're in this regime, it's basically high variance. Stuff we haven't talked about is all of this, but that's the end of the talk. I'm open to questions. Yep.
So one thing that you didn't mention is sparsity, which is when you have, well, if you're thinking in 2 dimensions, when you have points that are pretty separated from each other.
Yeah.
And that's when you have problems when finding a model that fits that, right? So you generally have a very high error rate. So do you have any insights on how to find this trade-off between finding a model that minimizes the error, but also that doesn't
overfit?
Yeah, exactly.
Yeah, like that's the key basically. So I mean, that's what you do here. If you split your data, as I told you, like if you have 3 sets and so on, and you plot these curves, an overfitting situation occurs over here. What happens is that your training error is like really low because you have a really complicated model, and errors on the training data, they just don't occur. And when you feed it new data, it's overfit, so then you have like the cross-validation errors are really high. So now you know that your model is way too complicated for the data that you have. So you like decrease the complexity of the model a bit, and you end up here, and that's the nice regime.
Okay, that's like an iterative by hand approach. You can automate.
Probably, yeah. Yep.
I have a question about clustering. And in particular, actually two questions, please. The first one is a more technical one, and is about the clustering package you used. In particular, I know that SciPy already has a module of clustering, hierarchical clustering, k-means one. Yeah.
Yeah.
To the best of your knowledge, do you know that if there are some differences with this scikit-learn clustering module or not?
No, I don't know the specific differences between the scikit implementation versus the SciPy implementation. So yeah, those differences you'll have to look up on your own.
And actually, does scikit use SciPy?
Yeah, it uses some of SciPy. It's on NumPy. So yeah, in the end, it's all down to. Yep.
Just the other one. Do you know if scikit-learn allows you to implement clustering or use clustering algorithms with data that are not represented as vectors in a geometrical space?
You will, like, input to everything in scikit-learn is vectors basically.
Okay.
Yeah.
Thank you for your talk. I really enjoyed it. So I have a question. So when you have a labeled data and you have a curve like this, what if it would be like this with the local extremums? So how you would know that you are not in the
For
local...
non-convex functions?
Yeah. So you're picking the... it's the third slide or fourth probably.
You mean the error curve? Okay, I think
it's in the very beginning. Few next slides. Two slides forward. Oh, this one, for example.
This one?
Yeah. So what if the curve would not be like this and would have like?
If it's irregular?
Yeah.
Yeah. So basically in optimization you have either a convex function or a non-convex function. So a convex function looks like this, and you can find the minimum of a convex function by basically just like gliding down this bowl. Optimizing a non-convex function is much harder, and some of the methods that I know are like simulated annealing and like the more heuristic kind of things. The more heuristics based methods, that's what you use to like optimize a non-convex function. So I don't know if you're familiar with genetic algorithms and things like that. So yeah.
Thanks for the talk. You talked about LSI for finding similarities between text documents.
Yeah.
I assume it can be done when we have all the documents at hand, like in the beginning. Is it possible to use it when we have a stream of documents coming? You want to process a stream of documents.
So you mean it's impossible to compute the LSI representation of the documents, or what?
Yeah. So I mean, with new documents, we have to compute this matrix again.
So there is a vector that corresponds to each document, and the document itself is usually not large, right? It's either a web page or a tweet or something. But you have a continuous stream of them, so you can like basically just keep computing a vector representation of every document, and you can store that on disk.
But I mean, maybe with a new document, some new keywords got introduced to the system that are not already in this matrix.
Oh yes, I think, I get what you mean. You need all the documents beforehand before.
Yeah, exactly.
Yeah, that's true. That's a limitation of LSI. So in that sense, processing text in real time, that can be quite a challenge.
Okay.
Yep.
One more question. So the example with the films and users. So it assumes that the X is actually related. So for example, you have semantic and action.
Yeah.
So what if, how to pick those metrics? So, for example, how do you know that Alice didn't pick the film because of actor, not the...
Yes, yeah, that's a good question. Essentially what you're asking is that in my example, I basically told you that romance and action are like good features for movies, which sort of makes sense. But if you have like data for which you cannot imagine what features are, then how do you like arrive at the features? And that's basically in machine learning literature called a feature learning problem, and that's like a whole field in itself. And
Okay.
yeah.
Great talk.
Thank you.
What to do? How vectorization works if you don't have inactive function? I mean, for a value of x, you can have multiple variable of epsilon or beta.
Of what? Of epsilon?
If you have for one value of for multiple value of a variable,
Yeah.
you have the same output in the function, or the way around.
Like what kind of situation are you talking about?
Houses with 200, 400 and 600 feet cost the same price.
Yeah.
Okay, yeah. So essentially, I mean, what happens is that there is variation in the real world, right? Like with the same input, you like the same output can have like different inputs, and the essence of a learning algorithm is to basically, when you feed it data, you don't want it to like memorize that a 200 square foot house will cost like exactly this. You don't want the memorization to happen. You want a generalization to happen. So essentially what you do is you get like, the idea is that as you get more and more data in aggregate, you will find out that for a given house area, like what is like the approximate good predicted price. Of course, you will never have any learning algorithm that can give you like the exact price. The idea is to be statistically correct, not correct on every data point.
And if you cannot learn enough, it means that it's not a good predictor of what you are trying to learn, basically.
Hi, thanks for the introduction. Do you know any Python tools, toolkit that use GPU accelerated technologies for machine learning?
No, but I know that there is PyCUDA available. So, yeah.
Hello, thanks for the talk. Just a question. I would like to ask you if you use scikit-learn in your lab, and if the answer is no, what is your opinion about the performance of scikit-learn compared to what you use?
So I actually use scikit-learn to basically build like a model of a communication channel. So what I'm trying to do is we run quite a lot of communication. So we build like modems that work underwater, and whenever you want to test something out, you have to like go out to the lake or to the sea and like test things. So a good example of a machine learning would be to have a model of a channel, like a statistical model of a channel, and that will tell you like how the channel will respond to different signals, and I built that using scikit-learn. And it works pretty well, but like my data is not huge. So if you're Amazon or Google, then you probably want to rethink how you're doing things. Yeah.
One more question is how you ever choose the candidates for model candidates? I mean,
Yeah.
the degrees. So you the very last slide, not the very last, but
Yeah.
at the end. So you're saying like pick the 10 candidates and calculate the average
Yeah.
error.
So essentially, what you do is like you learn the parameters for all the models using JTrain, using the training data.
Yeah. I mean,
then there's
how you ever pick those 10?
how do you pick those 10?
Yeah, how you determine that those 10 are candidates, like.
Well, I guess that boils down to your your intuition about the problem. So if you think that functions that look like these are a good representation of your data as it gets generated, then you use those functions. If you think that some other function, so for example, if you remember the logistic curve, the logistic regression curve, which is like an S curve, if you think your data is basically, if it looks like that and that function would be a good representation, then you choose that. So really what form of edge to choose, it really depends on your intuition. But like today, the most promising ones are neural networks and support vector machines, and they have really complicated forms of edge, but you don't need to know them to use them. So.
Okay, thank you.
Is it possible to get the slides you skipped?
Okay. The slides I skipped, I didn't skip anything. Those are backup slides actually. They're not part of the talk. Yeah.
That's probably the last one because we are running out of time. Well, I want to remember everyone for the Google Code Jam this evening, and thank you.
Thank you.